let's start for the tutorial for today. And I will demonstrate like how you can solve the rop-3-32 and rop-4-64. And let me share the screen. So all our challenges are on like a BMCTF2 machine, because this machine is running as a 64-bit and enabled with the ASRL. So you can enjoy the ASRL and DEP. Those defense mechanisms are active in combination. And we go to the challenge directory. And then we have a week 5 directory here. So you can run fetch week 5 to get your directory. And then we'll get to the rop-3-32. Yeah. And then to start solving the challenge, let's take a look at the source code. So in the main function, it does two particular things. So one is that it will change the directory to the slash. And then the second thing is like it will disable the path environmental variable. So it will just remove the data in the path environment variable. So like no matter what you set as a path environmental variable, so it will erase it. So you cannot play the path tricks with this. And then what will be the effect of this one? Change directory to the root. So what it actually does is something like, so previously we find some of the character at in the program or something, and then we symlink bin.sh to add, and then we can run this add program, then it will run the bin.sh instead. So we can do this kind of the trick when if we can find some of the strings in the program. But so what this change directory root does is it will start with change directory to the root first. Then like the what that means is like if we just put /add or add, then that will be like a class placed in this directory, which we do not have a write privilege. So the problem is like that we don't have a write privilege here, so we cannot write any file. So we cannot reuse some of the strings like this. Instead of that, we need to put our entire path for referring some of the files. Yeah. So what this makes is like it will not let you use symlink or like using the shortened file name for reusing some of the existing string in the program as a file name target, because your current working directory will be changed to the root. So you need to specify the entire path name. Yeah. So you have these two restrictions, and then it has a simple buffer overflow vulnerability here. So in the input function, what it does is it will get the data, which is definitely bigger than the size of the like a local stack buffer. But the interesting thing is that after receiving the buffer, it will copy the entire 1024 1024 bytes to the global variable buffer. And then this global variable buffer is defined as a size 1024. So there's no problem for the buffer overflow here, but only the buffer overflow here matters. So there's a little bit of description of the challenge, and then this challenge is all about. So you know that there's a buffer overflow vulnerability, but the problem is that where do you want to jump to? And then in the previous challenges, we try to use some of the functions such as execve or open, read, write, but we cannot find any of like the open nor the execve or system functions here. And because the ASRL is active, so other than like the functions listed in here, you don't know where the address is. So only the part of the program's code itself will be fixed, and then all the other areas, a library or stack, or like heap addresses, these will be randomized on each of the execution. So we must stay with reusing some of the functions here. And then there's an interesting function called mprotect. And if you get to the main page of the mprotect, then you will see the description. And then the important thing is like it will set the protection on a region of the memory. That means you can change the protection or like the runtime privilege of the certain memory blocks. And then, so the syntax of the using mprotect is like the calling the mprotect, and we can put the target address, and then for the length, and then protection level, then this system call will change the privilege of the memory. And then in the protection permission, it has read, write, and execute. So for the stack addresses, we know that it only has a readable and writable flags. And also for the global variable area, we only have a readable and writable flags. But using mprotect, we can actually add the executable flag to the region of the memory. Then we can indeed make that memory region as an executable. So that means originally your global buffer is not executable at all. But if we call mprotect to enable executable permission to the global variable area, and if we can put our shellcode in here, then we can execute that. So we will do that. And that's why this program is designed to have an mprotect as a internal function. So you can use that and utilize that to run your shellcode. So that's the exploit sketch. And let's try to write an exploit. So writing a Python script with all the Python tools. Then we will use rop-3-32, and then we will prepare a buffer. And before doing that, disassemble the input function, and then this is the read function, and then the buffer comes from the EBP minus 98, yeah, and then this might be the memcopy, and then this address would be the global buffer address. So if you don't get like why this is a memcopy, then please try to analyze what each of the instruction means. Then you will realize that from here to there, yeah, these instructions are actually doing the memcopy for the copying the global, copying the buffer data to the global buffer data. And then to check what's at this address, then that's address, that address is exactly gbuff. And then if you want to check, if you cannot get the address from here, then you'd like to know about like what's the address of the gbuff, and you can try it something like so XX address of the gbuff, then it will print out that here. Yeah. So we know that the two offsets are important. So one is like an EBP minus 98. That's our buffer starting position. And then the address of the gbuff is at here. So buffer is at EBP minus 0x98. So we have our buffer as buffer as a size of 0x98, and then save the EBP will be here. And then what we will do is we will call mprotect, and then return to somewhere, and then first argument as a target address, and then our target address is like the address of the gbuff, and then second argument as a size, so we will put 1000, and then third argument as a protection permission, and then if we set the read, write, executable, then it has a bit. It is each bit for indicating whether the permission is on and off. So for example, if we enable all three permissions, then 111 will be the value 7, and then read and write and not executable, then value 6, 110, and then read, not write, and then executable, then value 5. So the syntax is something like this, but we will enable entire permission. So we will put the 7 as a protection permission. So we will fill buffer with the 98 0x 98 bytes at the sum of the dummy filling padding, and then add save DBP, and then address it then protect. Then we can get the address of the mprotect from the p.elf symbols protect. Then we can also get the address of the gbuff p.elf symbols. Then what we will do is like we will not sending our buffer like this. So what we will do is, so in the code, we are seeing that our input goes to the buffer. And then that will be copied by mcopy. It was the execution was something like this. So our input actually will be placed at the global variable gbuff. So what we will do is, so instead of filling the buffer with A's, we will put our shellcode here, and then filler, and then entire size as a 0x98. So for example, we can put our shellcode. I prepared my shellcode here, so you can use your own shellcode here, and then I will put shellcode at the start, and then we will create a string as a. So we need to fill the number of A's to match the entire shellcode, and then padding size as a 98. So we can do it like this, and then it will fill the EBP, save the EBP, and then address up them and protect. And to write a ROP chain, we can make it as a cut it like this, and then after putting the address of the protect, we can put the first argument address of the gbuff, and then second argument has a 0x1000, then third argument is a 7, but in between the this and the first argument, we need to specify like which address we need to jump after running mprotect. And then we put our shellcode at the start of the buffer, and that will be copied into the buffer and then copied into the global buffer. So if we jump to the global buffer, then it will execute our shellcode. So we put the address of the global buffer here. And it will call mprotect with these 3 arguments and then jumps to where our shellcode is. That's the exploit. And then the one caveat of using the mprotect is like we need to put the argument as a page aligned address. And page aligned means that the size of the one page is exactly 0x1000 bytes, so which is 4096 bytes. And then to make that, we need to zero out the last 3 digits of the hexadecimal digit of the address. So what it actually do is like we have the address something like 8048.060, and then this operation will clear the last 3 digits as a 0. So we are using this value as the argument of first argument of the mprotect. So by doing this, so our execution will be, so it will firstly return to mprotect, and then it will run mprotect with these 3 as an argument to make the global buffer as an executable. Then we will jump to the global buffer and expecting that it will run our shellcode. And let's take a look at if this actually runs our shellcode or not. So to do that, we can send the buffer and then and set the p.interactive, but at the same time, we can debug the program. So to check if it runs correctly or not, we can attach GDB for that. And to do that, we need to copy the binary program to something else like this. And then we need to set the context. Use tmux and then split w. And I will get into the tmux session. And to follow the ROP chain, because our return-oriented programming will start at the end of the input function. So we will set the breakpoint at the end of the input function. So by doing this, we can set the breakpoint at the end of the input function automatically, and we will follow the execution. So I will run it. Then, oh, so it has an error. So address of the gbuf is not defined here. So what I can do is, so right now I use the variable as a addr gbuf. So I can change this as addr gbuf and run it. And our debugger is stopped at the sum of the read function. And then if we continue, then it stops at the return of the input function. And then our first return is to the mprotect. And then let's check the stack. And this is the address of the mprotect. And then this is the address that we will return to after calling the mprotect. And then this will be the first argument, second argument, and then third argument. So we are calling mprotect. So this address with the argument 80 for A000, and then 0x1000 as size, and then 7 as the permission. Yeah. So after calling this function, we will run this location 8048060, and then that's actually where our shellcode is. So it will put 32, which is get EGID, and then into 0x3080, yeah, and then set a EGID, and then exec BE, BNSH. So our shellcode, and then all the A's are here because we put lots of our. So maybe we can do this. So we put lots of shellcode and then lots of A's. Maybe we can reduce the size. Then so you can see the shellcode here, and then lots of A's at here. And then at the end of the buffer, you will see that the the arguments that we put for the mprotect are placed here. Yeah. So we are jumping to this location. So let's just follow the mprotect. So right now we are running the mprotect. So move on to next. Then it will jump to the real mprotect function, and then it will set all the registers and then call the system call. So this call to GS0x10. I didn't explain it anywhere, but in 32-bit machine running on the 64-bit Linux. Yeah. So the using this kind of the instruction is equivalent to the calling into 0x80. So this is a way to call a system call using a function call manner. Yeah. So so it's about like calling mprotect system call. So the EAX 0x70, that's the system call number of the mprotect, and then its second argument is the target of the address that we set as an argument. Third argument is a 1000, as a hexadecimal integer, and then fourth argument as a 7. Yeah. So it will run and protect, and then return value of the system call was 0. That means it was successful. And then I will just type vmmap here. Then right now our code area. So 804A000 from here to like a 1000 hexadecimal bytes. Yeah, we have read, writable, and then executable page here. Yeah. So because we changed permission, so previously it was RW and no executable, but it will be changing to RW and executable. Then I will show this again. So run it and continue, and then before calling the mprotect, we have this address and memory permission as RW, right? Then if we run through the execution, and then it gets to the calling of the mprotect. Then before having a system call, still we have a readable and writable. But if we run the system call, get the EAX as a 0, then our vmmap says like it's a readable, writable, and executable. So right now we change the permission of the mprotect, and then it will return to our shellcode. So it will run get EGID, and then we'll run set EGID, and then execve -h. So finally, it will run the shell from the exploit. But right now that we are with the debugger, so it shows our GID only. So in such a case, after checking that if the entire exploit works well with GDB, so we can change this with the regular target program execution. And then if you run it, then we can get the shell. So the challenge in this program is that it will change the directory to root and then set env to something else. So maybe you can think of like the trying some of the brute force attack as if like this is some of the challenges in like the ASRL 5.6. Then you may try, but the problem is that you cannot play with the path and then path tricks, or even you cannot use like some of the relative path names. So to avoid that, what you can do is like inside the program, it fortunately use the mprotect the system call inside of here. So you can call that function to make your global buffer address as executable. And by putting your shellcode on that there, so you can jump into there and then get a shell out of it. Any questions to this challenge?
Professor, I have a question.
Yes.
Because
yes.
In the code, we are change directory for the root. So that means I cannot make a code dump.
That's right.
Oh, I understand.
Yeah. So you don't need core dump if you can attach to the debugger. Yeah.
And then one more thing, because
yes.
in a challenge, the previous challenge, we usually use the pop return.
Yes.
But in this challenge, we don't use it. Yeah, could you please tell me the
because that is not required. For example, so the reason why we use a pop return, those kind of the clearing instruction, is to clear the arguments that we place it here. Yeah. So right now we only call two functions. So the first function is mprotect with these arguments, and then second function is our shellcode with the 0 argument. So in this case, because the second function does not require any kind of arguments, so we can directly call it. But if this excuse me, second call requires an argument, then what we can do is we can change this as a pop return. Then it will pop these 3 arguments, And then we can put the address of the global buffer at here. So this is a special case because our exploit chain is quite short, just calling the mprotect and then directly jump to the shellcode. That's why I didn't use a pop return here. But in case if we need clearing the arguments, then we should use pop return here. But in 64-bit, because you need to set the register values for the argument passing, so you might need a pop RDI and pop RSI, pop RDX return for that purpose. And any other question? So your exploit might not working as a one shot, so please don't give up. And then also please actively use this kind of the debugging capability that you can see any kind of the value transition and also follow the execution by instruction. And if it goes in an unexpected way, then you can figure out where it diverges from, and you can adjust the values accordingly. Yeah. So after watching this, I believe I'm sure that you can easily change this kind of the exploit to the 64-bit version. So the only difference is a little bit of matching of the blocks of memory to the 8 bytes. So you should use a P64 instead of the P32. And another different thing is the argument passing is based on the register values. So, and then let's move on to the rop-4-64. So I will for this one, I will demonstrate the solving of the 64-bit challenge, but you can apply the same technique to the 32-bit one. And in this challenge, so it does the same thing, the change directory to the root. So you cannot refer to the files in the relative path. So you should use the absolute path for the pointings of the files. So basically, to read the flag, so the task of this challenge is you need to run open, read, and write. Yeah, and 3 system calls, 3 library calls, but you need to point the file name as the absolute path. And then it also disables path environment by putting the bin as the user bin as the path. And then inside the program, we will have 2 functions, the string copy and open. And because, so in the input function, it has a very simple variability here. So it is a read function, and then it reads up to 4096 bytes, which is far bigger than the buffer size. And then in the rop-4-64, so for writing the ROP chain, you need to figure out what kind of functions that you can utilize, and then the functions that we may use is the maybe puts for printing out some of the string to the console, printf maybe, and then change directory and set env. These are hard to use in the the writing exploits, but we can use read and also open. So from these kind of the setup the functions. So we can use open, read, and printf for opening the flag file and read that from the file to the memory, and then print out the flag data to the console. So in that case, the challenge looks similar to the week 4 DEP3, which we call the sum function, and then it does internally it runs open for us, and then read and printf. And in the rop2 challenge, we need to call open, read, and write, chaining 3 functions. So we will do the same thing, chaining open, read, and printf. But the problem is that this one. So what we will do is we will run open something, then read 3, sum of the buffer, and then size, and then printf buffer. and this will read from this file, and then we will print that out to the console. Then previously, we can use any kind of string at, and then try to get a symlink from the flag to the character at, or like some of the main, which exists in the code area of the program. And then we can reuse that as a string to open the file. But the problem is that right now we have a change directory factor here. That means like even if we refer to the main or add file, then that will be referring to the file in the root directory here. But we cannot create any kind of file here. So that's the problem. And then that means to read this flag file, we need a full path of this and /flag. And then we need this kind of a string in the program's memory space to open the file, because our current directory is fixed to the root. So we cannot use the relative addressing. So we need to supply the entire full path as an absolute path. That's the restriction here. And I want to teach you one of the interesting way of using ROP with the string copy. So because basically what we will do is like we will build this string by using some of the existing string literals here, and using string copy. So basically we will copy. So for example, if we want to build a string sh, then we will copy from here to there. So starting from s to the this string to somewhere for the first character. And then if we need to copy h, then we can copy entire this part as a second character position. And then maybe we need to put the slash, then we can find some of the slash data here, and then copy that to the right next to the buffer. So what we will do is like we will use the ROP chain to build a string with the string copy first, and then after that we will use that as a following function call open read write. So let's start writing the exploit script. So we will open the process rop-4-64, and then before exploiting the vulnerability, we need to check where the buffer is. So the buffer is at the RAX is coming from RSI is coming from RAX, and that is at the RBP minus 0x80. So we know that our buffer need to be 0x80 and then some 8-byte saved EBP. So our buffer will start here. Then we can add some of the return address and doing something. And what we will gonna do is like we will first build a string, and then right now to not to leak the flag in this console, I will create the fake flag. So I will create a fake flag, and then it's stored in the file name and flaag. Yeah. And then because we need to use the absolute path, so the full path of our fake flag is this one. And then what I'm gonna do is like that I will try to read this file during the execution of the rop-4-64. So our target string is this one. Yeah. Then target string. Then we will build this one, build the string by using the string copy function. And to do that, we need to get the string copy first. So address of the string copy is here. And then we need to get some strings that we can reuse. So for example, from the input function, there are several puts, and then it will print out some of the strings. And then the one interesting thing about this string is that this string contains all the A to Z characters and the lowercase. So I intentionally put this string because you can collect any kind of the character from here. Yeah. So we need this address, and then also we need another address for the numbers. So maybe so if we increase some of the offset, then we can point here. Then we can point some string addresses that contains number. So we can copy these information, then put the information at here. And what I will gonna do is, so we have an alphabet string here, and then we have a number string here. And address of alpha will be this address, and then address of the number will be this one. And then another thing is, so we need a target address. So what we will gonna do is like we will copy the string from these two existing string, and then per each character and number dash, or like we will also find the slash in the program too. Yeah. Then we know the copy source address, and then we need to have some of the area that we can store some of the string. So we can get that from the GDB. So break and main and run it. Then from the VM map, we can see that this readable and writable area. So we can use any address and 601000 to like 20000. So as we did, so let's use 601800. And then check if like these are all empty. So this is just an empty area, so we can use it. So we will use this address as a target address. And then let's search for the string slash, and then to fix that to your module. So by running this command, search character, then binary file, then it will search this character in the memory space of this binary program. And then it will print out several values and this address, 400398. So it says slash. So that's the exact slash. So right now we have two addresses. So we will copy all of this. So we don't need this information. So we will use the address of the string as the somewhere in the global variable area, and then address of the string slash is that here. And then what we will gonna do is, so we collected all the information, and then we will write the code. So for I in so we will loop over the target string, and then so we get the first byte at each byte of the target string, and then if that is slash, then we will set the source address as the address of the slash. Then if we can find the character in alphabetical string, so that means like if we meet the character H, then like we can find H in here. Then if we run this string, the alpha string, find C, then it will return the index of the first occurrence of the character. So if we if we supply H to the alpha string that find and then character H, then it will return 1, the position 0 and 1 as the first find. And then we can get the address of this string by adding the address of the alpha on it. Because this address points to the starting address of the string, and then because this alpha string that will find the first occurrence of the offset in the string. So by adding these two, so we can get the actual address of the character like this. And then if maybe we can connect this as an else and if. Yeah. And then if that is in number string, we can do the same thing. Source address could be addr number plus number string find C. And no matter what kind of character we have, if it is like the lowercase, then it will be found here. And then if these are number, then or dash, then it'll be found at the string space, and then added to the source address. And then we will have a target destination address, and then destination address is like we will actually build a string by each byte, byte by byte. So the address of the string is there, and then we will use I as an index. So for I0, so we will put at the 601800, and then I1, for I1, we will put the next character as a 681801. So it will paste the character by character to build out the string. And then actually we need to make a string copy function call. So our block for string copy is that we need to set the what we want to do is string copy destination addr and source addr. So for example, if we put strcpy 601800 and then address of this one, then it will store character s to the string 0 h. And then if we run string copy 0x61A1801, and then maybe this string, then it will put string 0 as a h because we didn't change the string 0 because the address is a 01, and then string 1 as r. So we can actually put any characters by pointing this index and also copy the entire string right next to the existing string. So we will basically do string copy destination and source. And to do that, we need to figure out like how we can put the arguments. So to do that, we need to run the rop gadget. Then from the rop gadgets, we can get a little bit of like a useful stuff. And so string copy open read write, it requires 3 arguments at maximum. So our interest is like getting RDI, RDX, and RSI. So we only need these 3. So we will create pop RDI return as this address, pop RSI R15 return as this address, then pop RDX RBP return as this address. Then what we will call is, so we will first set the first argument. So P64 pop RDI return. And then we want to set the destination address as the first argument. Then we will set the second argument, PRSI R15 return. And then second argument as a source address that we calculate from the relative position in the string. And then R15 as any kind of value. Then we don't care about the RRDX for now because we only supply 2 arguments. And then call string copy. And then we will attach this block to the buffer. So what we will gonna do is, so there's a buffer, 0x80, then save the EBP. Then right next to this one, we will call pop RDI return. So RDI, and then first argument as a destination address. And then, so I can write an offset as a 0, and then RSI R15, then RSI as a source address, then R15 as a 0, and then call a string copy. And then we will do this for many times for index 1, 2, 3, 4, 5. And then by changing the source address for many other places based on the target string that we need to make. So for example, our target string is this one. Maybe I can collect all these addresses here. So for the first part, so we will set the destination address as this address, and then the source address is 0. So pop RSI R15, and then source address is 0 as the first character, which is a slash. So we will put the address of the slash at here, and then call string copy. So it will copy the slash character to the position 0, and then to the position 1. It will call string copy to the source address 1, which is the address of the H, will be the entire string of this one, will be copied at position 1. And position 2, it will copy the character O. So starting from here to there, and this will be pasted at the here. And then we will do this again and again. So that's why I wrote a loop to attach this kind of the string copy again and again. So after executing this as a chain with the chain of the string copy call, so we can build the string at the this address. And after that, we can call open, read, and printf. And then let's do that. So to do the let's do the open function call first. So we want to open target string 0, 0 first. And to do that, we need to set up the buffer as p64. We need to set the first argument, pop RDI return, and then we need to set the first argument as a target string. That's the ADDR string, maybe, right? Yeah. And then we need to set the second argument, PRSI R15 return 64, then 0, 0 for the R15 too, and then P64 pop RDX RBP return. We will set the 0 for the RDX2, 0 for the RBP2. So this will set the all 3 arguments, and then we will call open. Then we need to get the address of the open, read, printf here too. Open, read, printf. So we will get all the addresses. So we will call open here, and then next we will call buffer and size. So we will call read with the RDI return first argument as a file descriptor 3, because file descriptor 0 is for standard in, 1 is for standard out, and 2 is for standard error. So the first file you will open will be we'll have a file descriptor number 3, and then RSI R15 and return. And then for R15 we can put 0, but we can put any kind of the writable address. But we already know that we have a one writable address at the address of the string. So maybe we can use another address of the buffer as a address of like this address plus 100, maybe this value. So we can put the address of the buffer here, and then rdx rbp and return rdx as a 100 as a size, and then 0 for the rbp, and then call the read function. And then finally, we would like to call the printf, then printf buff. So to set the first argument, RDI return, and then P64 for the first argument buffer as the address of the buffer here, and then call the printf. So basically with a loop, and then by finding all the characters from these strings, and then having a slash, so we can build a string of the file name here, and then we can run, open, read, write, printf. So we actually build a long chain of the ROP chain, but because it will run as a execute, pop, return, pop, return, so it will run as a chain. So this challenge actually demonstrates the capability of the ROP that you can run multiple functions in chain by running the several calls to the string copy to build the arbitrary string. And then let's check if it runs correctly. I know that this exploit is incomplete, but I will just run to check if it runs. Then to do that, add the context, and then so I will copy the binary, and then I will break at the end of the info function. So get the address of the info function here. Set the breakpoint there. Then we will watch how it runs. And then we need to send the buffer, make the program running for our debugger. Then let's see how it runs. So in the debugger, I will just continue. Then now it was it stopped at the end of the info function. And what we are doing is that we will set the two arguments of the string copy and then run it. So the first return was to the pop RDI and return. So it will pop RDI and RSI, R15, then return. So now we are at the string copy. Then let's see how our stack configuration would look like. So these are like a 10 printout from the stack configuration. So this will be the return address of this, the return address of the after the running the string copy, it will return to this address, then which is as a pop RDI and a return, because it will chain as a popping the argument and then call string copy and again. Yeah, and then it's the first argument. RDI has a nothing, so our RDI is set as the target string address. Then our RSI is set as a slash. So what it will do is like if you type return in the function, then it will run until the return of the string copy, and then it will return to the pop-up return again. So right now, so in this string, it has nothing as a value, but after running this string copy again and again, it will copy the value to the target string location. So if we continue the program, so there's an error. Yeah, sorry about this error. So let me debug it a little bit more. No. So we put the address of the string as a 601800. Then destination address as that one. Yeah. So to see that, let's debug the program again. So this is the first return, and then it will return. It will set their RDI and RSI R15, and then return to the string copy. And then after running the popping their RDI and RSI, yeah. So our RDI is a 601800. Then RSI is this string. Then at the end of this string copy call. So string copy now finish it, and then at the target RDI, we have a slash character here. Yeah, and then we will move on to the next character. So right now our RDI points to the 01, the first position, and then the previous value was 0, so there's nothing on there. But on our RSI, we have an H, because what we're going to build is a slash HOME, those characters. So it will attach H as the result of the execution of the string copy. So let me break at this address, continue it, then. So right now, starting from the RDI, so it pasted this much of the address. So actually, so if we print out the 601800, then that will be /H, but the rest of the characters are like something meaningless thing. And then we will call this string copy again and again. So for example, so right now is quite weird. So the debugger is messed up with the execution. So basically what we are doing is like we are creating this kind of string by character. Yeah. And then after creating all the string, so we will use that to open the file. Yeah. And then read it out. But when you use printf, if you have some of the problem of the crash on the printf, for example, so if you continue twice, then it has some of the problem of the printf. That means like your addresses is somewhat misaligned. So because this MOB APS, this instruction requires addresses of the RSP need to be aligned as 16 bytes, but the last digit is 8. So you need to push your stack 8 more bytes to make it as aligned to be 16 bytes. So that's the specific instruction for this MOB APS. So other than that, like you cannot pass this kind of execution. And in the regular execution, because all the stack formation is matched to the the function call and return, so it will be always aligned to the the multiple of 16. But because we are creating the ROP chains with the arbitrary data, so based on our ROP chain, our stack movement will be single 8 bytes. Could be the multiple of 16s for sometimes, but for other times, it could be like any kind of the arbitrary bytes. So what we can do is like we can push the stack one more time, and then to do that, so what that means is like when we execute the printf, our stack is not aligned by the 8 bytes, 16 bytes. So what we can do is we can put the address of return here, because that will push 8 bytes, and then it will just return to this address. So to find that, we need to find the address of the return from the ROP gadget. So address of the return is at here. We can use this as another gadget. So by placing, so we can place as much as we can of like this kind of the return address, address of the return instruction itself, because it will return to the next instructions. But doing that will match the alignment of the printf. Then by running this, so it says like there's an invalid instruction set here, but at the string here, then you will see that it built the entire string by copying each character by character starting from here to there. But the problem is that it has the flag, but it has a what is that? Exclamation character here. The reason is like it doesn't cut up the string very well. So to cut the string, what you can do is the end of the string is actually the 0x00 bytes. And then that's actually attached into the each of the character string. So what we can do is like we can put that 0 bytes here, then like our loop will for the if it finds the 0 bytes at here, then it will automatically find the tailing 0 bytes here and then returning that address. So copying the null string to the target address will create the exact flag location. So that means they continue multiple times. Then, so if we try to check the string value at that location, then we can see that the string copy successfully generate the entire string value like this. Then we can read the flag inside here, like this. So I didn't demonstrate this with the real flag, but by changing the flag location to the other one, then you can read out the flag. But here is that I chained the ROP chain for multiple times. For example, what is the length of the entire this string? So for example, so 42. So I chained this string copy ROP chain for 42 times to build the string for the path name, and then use that to open the flag file, and then read and printf to get it out as a console output. So basically the lesson here is that by chaining the ROP gadgets, so you can call arbitrary number of functions with the arbitrary arguments. So this example is for like a chaining the string copy for many times. And then you can build any kind of string because ROP is Turing complete. And you can call, after that, you can call these three functions to read out the flag. Any questions for this challenge? So the important part is like the stitching all the strings from the borrowing the characters from the each characters from the binary program. So you can actually build any kind of string because if there's any kind of the matching character inside the binary program. And the challenges for the 32-bit one is just a counterpart of this one. So that you can actually do the same thing, calling a multiple string copy in 32-bit 2 in a different fashion, because you need to supply the arguments to the stack, not by the passing the values to the register. So that's the only difference. And I believe based on like the solving rop-3-32 and then rop-4-64, you can also solve the counterpart of the challenges. And then on Thursday, I will cover the rop-5 and rop-6 challenges, and then that will conclude the end of the rop challenges, and then we will move to the week 6 challenges in the next week. Is there no more questions? All right, let's finish tutorial today here, and then I will upload the video and then provide the link accordingly.
Professor, I have one question because
yes,
in week 5 there is also extra challenges, 2 byte and 1 byte, something like that. Yeah, but I cannot fetch that one, so TA told me I can use the symlink that, but I cannot copy or the fetch is impossible. That how can I use that?
So for example, so we have a home and labs, not here. Is that on the VMCTF3? No, here, extra, right? Yeah. So you can create the symlink for this one. So for example, you can create the this directory as your home directory, like this, and then you can create the same directory too. There it is. So for example, so at here, what you can do is this into that directory. Then we can get into here, then no. So maybe you need to use the full path. And you can use this binary program for running. Yeah. So you can create a symlink to this program path under your any of your directory. So for example, if you have your shellcode writing directory, so for example, in week 3, maybe non-zero shellcode 32 or something. Yeah, there's a shellcode bin, but if you create a symlink like this, then you can run this, but it will not, this shellcode is not written for this challenge, so it generates a segmentation fault, but you can play with that.
Oh, thank you.
Right. So the fetch command is basically doing this kind of stuff automatically for you. But this extra credit challenge one is out of like a directory structure, like not like a week 1, week 3. So maybe if you try fetch extra, it does not work. Yeah.
Yeah, it does not work.
Yeah, right. In that case, like you need to manually create a symlink for that. Yeah. All right, let's finish it here, and then like please feel free to ask any questions on Discord. All right, thank you, and then see you on Thursday.